I recently came across this function here, and it just really caught my attention. I thought it was a nice function. If you go to plot it, it looks something like this. It has an infinite discontinuity. If you're looking for continuity, there's an asymptote at 2. How do we know that? Well, if you look at the denominator, you're going to see that if I plug in 2 here, this denominator is going to go to 0, and so we have division by 0, and we can't do that. So, one of the first things that I want to look at is what's its domain and range. This is a common question for an algebra class or maybe some other pre-calculus or even a calculus class. So domain and range. Domain is, in short, it's the x values. So if I put vertical lines through here, is there some place that I'm going to put a vertical line where I don't touch both the x-axis and the plot here somewhere? So the only place that I'm not going to be able to do that is where this break is right here, and that's occurring at 2. If I plug in 2 here, this is going to 0. So one of the things to look at when you have a function that's made of a fraction, what values are going to send the denominator to 0? Those are not going to be included in your domain. Alright, so I've used interval notation here to show my domain. So on my range, I'm going to do a similar trick to what I did with my domain. Range primarily deals with y values, so I'm going to do some horizontal lines and see if I can draw a horizontal line. And everywhere that I draw a horizontal line, I should touch both the y-axis and the plot, the graph of this function. Now, we have this big gap here, but coming straight out here, this is going up and hitting positive infinity. So even though there's a gap here and I'll miss on my horizontal here, I'm going to hit it over here, and so I'm still touching the graph of this function. So even though we're missing a value in our domain, our range is actually going to turn out to be all real numbers. Alright, so all real numbers, we have this interval. The next thing that I want to do is I want to find this x-intercept. We only see one x-intercept here. There's some complex roots that we could be looking for, but we're going to focus on the real root. So I want to know this value. So I'm setting my y value equal to 0, and I need to solve for x. This can be tricky. You can try to do some division and hope that once you make this fraction look less like a fraction, that it's going to be simpler. It doesn't turn out to be simpler. You might also try to do some factoring techniques with this numerator. That doesn't work well either. One thing that we can do though is take advantage of the fact that if the numerator of a fraction goes to 0, then the entire fraction is evaluated at 0. So instead of looking at the fraction, what we want to do is just look at what happens when the numerator goes to 0. Alright, so if we're looking at just the numerator and it being set equal to 0, this becomes a lot easier to try to find an x value here. So this is just going to be some simple algebra at this point. I'm going to add 7 to both sides, and then I'm going to take the cube root of both sides, and that's going to give me that x is equal to the cube root of 7. And so that's my x value. My y value is, of course, 0. If this is plugged into here, we have cube root 7 cubed. It's going to give me 7. 7 minus 7 is 0. That's my numerator. 0 divided by anything is going to give me back 0. So we're good here. So this point is now known. It is cube root 7, 0 for our x-intercept. We're going to look at integrating this function from 0 to the cube root 7. And so you might be looking at this and thinking, maybe I need to remember some kind of antiderivative, or maybe I'm going to use a u substitution. The thing that I did is I decided to just divide this out, and it's going to give me a series of terms that are added together, and so it's going to be really easy to integrate that. So that's my approach. Okay, so when we divide this out, we get these 4 terms, and then I'm just going to look at each term and establish its antiderivative. The first 3 are pretty straightforward. The last one is something that you're going to have to remember, that this is 1 over a function, and so we're going to get the log of the absolute value of that function. And then we're going to go in and substitute our values in. And when we substitute the 0 in, we're going to see that these first 3 terms are disappearing. This one doesn't disappear. You're going to get 0 minus 2, so you're going to take the log of 2 because we're taking the absolute value. Alright, so when we substitute these values in, we get this. A little bit of algebra is going to help us simplify this. So we're cubing the cube root of 7, so that's going to give us 7 back. We're going to get 7 times 3 is 7/3. And then we're going to square the cube root of 7, which is going to give us the cube root of 49. And there's nothing really to do here. This is as simple as it's going to get. We have 4 times the cube root of 7. And these we can use some logarithm rules on and bring this -2 here as a denominator. So we're going to get the log of the absolute value of cube root 7 minus 2 divided by -2, and that's the absolute value. So this is what we end up with. This is our exact answer. This is going to be approximately equal to 10.51. It goes on a little bit. There's some decimal dribble there. But this is not a bad value to have when you think about what we were looking at with the curve being there near the origin. 10.5 is a really nice number to come up with for an area. It's not too wild there. If you're looking at this exact value, that looks a bit nasty, but we can, I would say, get our head wrapped around this 10.5. I think this is a really nice problem to think about for an early calculus problem. It really brings in some of the things that you learn in a pre-calculus course, and you look at all these things that pertain to properties of functions, and you get into calculus and you start to think, well, maybe pre-calculus didn't help me prepare for calculus. But then you look at a problem like this where you had to find that your limits for integration, you had to find this cube root of 7 to be able to integrate properly, because you can't integrate all the way out to 2. There's an asymptote there. That value isn't in there. And if you remember back looking at the domain, we found that 2 wasn't in that domain. And so this really brings together our pre-calculus ideas and applies it in an early calculus setting. Cheerful calculations.